Today we will read how to minimize the Boolean function, but before that first we discuss the answers of the previous lectures quiz. The first question was to simplify the following Boolean functions to a minimum number of letters. First one was BC plus AC bar plus AB plus BCD. Okay, we will see first how we can simplify that. The expression is the 1A BC plus AC bar plus AB plus BCD. Now, if we take BC and BCD and BC common, then it will be 1 plus D, and we keep, because no literals are common in between these two terms, so keep as it is. Now 1 plus D is 1 from the basic postulates, so this becomes BC plus AC bar plus AB. This is a simple situation. Now we see the second one. Now the second question was that A plus C plus D, A plus C plus D bar, A plus C bar plus D and A plus B bar. We have to simplify this equation. So again, if we take the example 1b, this is A plus C plus D, then A plus C plus D bar, A plus C bar plus D and A plus B bar. Now, if we take the first two terms, then A plus C is common and D and D bar are different. So, this will become, if I apply the distributive law, then this is D bar A plus C plus A plus C plus D into A plus C plus D bar, and the last two terms keep, this is as it is. So, this will be A plus C bar plus D and A plus B bar. Now, see that here from the first three terms, if I take A plus C common, then it will be 1 plus D plus D bar, and D bar, this becomes 0. So, D bar equal to 0, then the remaining term will be A plus C bar plus D and A plus B bar. Now, this becomes A plus C because our d plus d bar is 1 from the basic postulates, and 1 plus 1 is 1. So, this becomes these two terms simplified to a plus c. Then the remaining terms a plus c bar plus d into a plus b bar. Now, again if we take the distributive law, then this equation becomes a plus a c bar plus a d plus a c plus c c bar equal to 0. Okay, then I write that thing c d. This is one term and multiplied by a plus b bar. Now, see, from the first term, this is a nice equation, and if I take two terms at a time, say a plus c bar, from here if I take a common, then this becomes 1 plus c bar, and say I keep as it is all the term ad plus ac plus c c bar becomes 0 plus c d, and then the a plus b terms, a plus b bar. Now, see, 1 plus c bar is 1. So, this becomes a, 1 plus c bar is 1. So, this becomes a plus ad plus ac plus cd, this into a plus b bar. Now, again I will take a common. So, this becomes 1 plus d plus ac plus cd a plus b bar. Now, from here again 1 plus d equal to 1. So, this becomes a plus the term ac plus cd a plus b bar. Now, applying the same rule, a plus ac becomes a, 1 plus c equal to 1. So, this becomes a plus cd. So, this becomes a plus cd into a plus b bar. Now, if I again apply the distributive law, so this becomes a plus a b bar plus a c d plus b bar c d. Now, from here a 1 plus b bar plus a c d plus b bar c d. From here 1 plus b bar equal to 1. So, again a plus a c d plus b bar c d. Now, again if I take a common, this becomes 1 plus c d plus b bar c d. Now, see, 1 plus c d, whatever this term become c d is, this equal to a. So, this becomes a plus b bar c d. So, mainly for this simplification, we have used the basic postulate that 1 plus b equal to 1. We have utilized this formula and we have simplified that equation. Now, we see that our second one. So, this for the second one we have to take the complement of the Boolean functions. Now, one by one we see that how we can, with the help of the postulates and the theorems, how we can take the complement. Here particularly the De Morgan's law we have to use. So, we see so the question number 2a is BC bar, even if you see this is BC bar plus A bar D. BC bar plus A bar D into A bar B plus A D. Okay. Question number 2a, B C bar plus A bar D into A B bar plus C D bar. Say this is my function f. Now, I have to compute the complement. So, if I take the complement f bar, then it will be the full bar, that means B C bar plus A bar D into A B bar plus C D bar, the complement of the whole thing. Now, if we apply the De Morgan's law or the duality principle, then what will happen? Actually, the two operators will interchange, that means plus becomes dot, dot becomes plus, and the complemented literals become the uncomplemented one and the vice versa. So, complement this thing. Now, we replace the two operators, that means plus will be replaced by dot and dot will be replaced by plus, and the complemented variable that would be replaced by the uncomplemented one and vice versa. So, the first part, that this becomes BC bar plus A bar D, complement of that this dot becomes plus, and then again AB bar plus CD bar, complement of that. So, if we take this as the f1 function and if it is f2, then again this similar to f1, f bar is f1 complement and plus f2 complement. Now, if we apply the same De Morgan's law, then what will happen? That the first term becomes that BC bar complement of that dot A bar D complement of that, it will be the first term. Similarly, this will be AB bar complement of that dot CD bar complement of that. Now, we apply the same rule and this becomes B bar, this dot becomes plus and this become complement of C, complemented of that thing, into dot that again A bar bar plus D. Similarly, this term becomes A bar plus B bar bar dot C bar plus D bar bar. Now, see that our complement of A, and if we take complement of that thing, that means A bar bar equal to A itself. This is our involution principle. So, this becomes B bar plus C. Similarly, this becomes A plus D, A plus, okay, this is actually complement, A bar bar plus D, A plus D bar this becomes A bar plus B, this becomes C bar plus D. And actually we miss the plus here, this is one plus, it remains as it is. Now further we can simplify these two terms, because if I want some standard form, that means either it will be some sum of product forms or the product of sum forms. See, it is neither the sum of product forms or the product of sums, because if I take only the first two part, this becomes the product of sums. Similarly, this becomes the product of sum. This is one POS, this is also one POS, but this is one plus exists here. So this is not any standard form. So if I want to make this as a standard form, then again we have to simplify further, we have to simplify it further. So this becomes F complement becomes, then if I put again the term B bar plus C, A plus D bar plus A bar plus B and C bar plus D. Now if we apply the distributive law, then this becomes B bar A plus B bar D bar plus C A plus C D bar. Similarly, this becomes A bar C bar, A bar D plus B C bar plus B D. Now this becomes B bar D, B bar D bar plus A D bar. So these two terms I keep as it is. And then B bar A okay, if I take this term again, this is a sum of product forms, this is a sum of product forms, but this can be further reduced. If I apply some of the minimization rules, then it can be further simplified. Now we see the second one, that 2b, that AB bar plus C bar D bar. We see that how it can be, we can take the complement. So this becomes, the 2b is AB bar, say F equal to AB bar plus C bar D bar. Similar way, if I take the complement, then it will be AB bar plus C bar D bar whole complement. Then this becomes AB bar, complement of that, plus this plus will be replaced by dot, and then C bar D bar, complement of that. Then this is equal to A bar and dot becomes plus, and this is B bar bar. Then this becomes C bar bar plus D bar bar. Now this is A bar plus B into C plus D. Now, see, this is my product of sum form. This is a product of sum. Now, we see the question number 3. Question number 3 is express the following function in a sum of min terms and product of max terms. In the last lecture, we have defined the min terms and max terms and the sum of min terms and product of max terms. So, now we have to represent AB plus C into B plus AC in that way. See how we can do that thing. So, this is question number 3, and the problem is that AB plus C into B plus AC. First, we take the sum of min terms. Now, again here we have to apply the postulates and the theorems. Now, first if we apply the distributive law, then it becomes AB plus ABC plus BC plus AC. This becomes this. Now, I will keep ABC as it is. Now, see, AB I can write AB into C plus C bar, because C plus C bar is nothing but 1. Similarly, when I take BC, I will add A plus A bar, and AC B plus B bar. So, just notice that when I am taking a term and I am adding some term or taking the product, then I am taking the remaining literal which is not exist in the term. See here AB, so the remaining literal C was not here. So, I introduced C in such a way that actually C plus C bar is 1, C plus C bar is 1. Similarly, A plus A bar is 1, B plus B bar is 1. So, I have, when A was not there, then BC into A plus A bar, similarly AC into B plus B bar. So, that I have introduced. So, how it becomes then this ABC plus, now again if we take ABC plus ABC bar plus this is again ABC plus A bar BC plus ABC plus A B bar C. Now, see all ABC, this becomes ABC because x plus x equal to x. So, again from the first postulate it becomes ABC, and the remaining terms are will be there ABC bar plus AB bar C plus A bar BC. So, this is my sum of min terms, because this is a 3 variable function, it was a 3 variable function. So, these are the min terms, the sum of min terms. Now, we see how we can write this thing as a sum of a product of max term. Now, before that, another way we can represent this thing, say the terms are A B C bar, A B bar C, A bar B C. So, I can tell that if the min term wise we can write say 0 0 0, 0 0 1, 0 1 1, 1 0 0, 1 0 1, 1 1 0 and 1 1 1. So, the last day we define these as the terms are M 0, M 1, okay. Another term was here 0 1 0. So, this is M 2, this is M 3, M 4, M 5, M 6 and M 7. Now, if I take the variables are A, B, C, then actually ABC means that my M7 terms. ABC means 1 1 1 means this is actually M7. Now, A bar BC means A bar BC means 0 1 1. So, this is nothing but M3. Similarly, AB bar C means 1 0 1, that is M5, and ABC bar is 1 1 0, that is M6. So, in the function given, the terms present are M7, M3, M5, M6. So, now we can write in this way that the function is f of ABC and this is equal to, as this is a sum of min terms, so this is sum of that 3, 5, 6 and 7. So, I can also represent in this form. So, this is also the sum of min terms form. Now, we see the product of max terms. So, if it is a product of max terms, then again question number 3, that AB plus C into B plus AC. Now, see here I can AB plus C. Again I can use some theorem that actually this becomes, we remember that A plus BC means if we apply the distributive law, so this becomes A plus B dot A plus C. Now, if I apply this theorem here, then I will be getting this is A plus C into B plus C. Similarly, the second term becomes two product terms B plus A and B plus C. Now, B plus C is same. So, this becomes A plus B, B plus C into C plus A. Now, I have to represent this as a product of max terms. Now, we see because already this come as a product of 3 terms. So, now we see what will be the first term, C A plus B. Now, what I can do in the product term, because C is not there, the literal C is absent in the first term. So, I have to introduce C. So, how I am introducing? A plus B, now here as if plus 0, as if this becomes 0. So, now 0 I can replace that A plus B plus C C bar, because C was not here. So, I have to introduce C, and in this way I can take this thing. So, now again if I apply the same rule, then this becomes A plus B plus C dot A plus B plus C bar. So, only the first term becomes the product of two terms. Similar way I can see B, what the B plus C and C plus. So, how B plus C becomes B plus C, as here A is absent. So, I can introduce A in the similar way as A bar equal to 0, and this becomes B plus C plus A into B plus C plus A bar. Similarly, my C plus A becomes C plus A plus B into C plus A plus B complement. Now, my F will be that A plus B into B plus C, what was there earlier, C plus A, this becomes A plus B plus C, A plus B plus C bar. This is for the first term. For the second term, B plus C plus A, B plus C plus A bar. For the third term, C plus A plus B, C plus A plus B bar. Now, see here A plus B plus C, A plus B plus C, A plus B. So, x dot x equal to x itself. So, again from the postulate, the basic postulates, I get A plus, this becomes A plus B plus C, and the remaining 3 terms will be there. So, this becomes A plus B plus C bar, then B plus C plus A bar, and this becomes C plus A plus B bar. So, this is my product of sum forms, product of max terms, product of max terms. Okay. So, we have discussed the answers of the last day's lectures quiz. Now, today we will start today's lecture. Now, as already we have seen that we will see the Boolean function minimization today. Now, for that first we have to discuss that Karnaugh maps. Now, before giving that actual definition, again we recapitulate that the basic Boolean operations are and or not. That means our complement, plus and the dot. Now, these operations can be combined to form complex expression. Just now we have seen many of this type of expression, which can also be directly translated into a hardware circuit. That also last class we have discussed. Now, Boolean algebra helps us simplify expressions and circuits. The theorems and the postulates we have read, using that we can always, but as last day I mentioned that there is no clear cut rule, that we have to apply in different way, and today's that the quiz questions we have solved, there we have seen that applying those theorems and postulates we can simplify those Boolean expressions. Now, today we will read that some rules or some methods, and this is called the Karnaugh map. First we define the Karnaugh map. So, Karnaugh map can be used to minimize the logic functions, so that it can be implemented with minimum number of gates. So, we will be seeing that it is a graphical representation of the Boolean expressions if it is in some standard forms, either it is a sum of min terms or product of max terms, because always the product of max term can also be represented by sum of min terms. Then graphically if we represent, then there is some rule that we can simplify this expression with minimum number of letters and the operators, so that with minimum number of gates the function can be realized. Now, there are a minimum number of product terms in the expressions. So, what do we mean by this minimization using kernel maps? That minimum number of product terms, and each term has a minimum number of literals. So, just now what we discussed, just applying the postulates and the theorems, then now today we will be seeing a well defined graphical method by which we can minimize the Boolean expression. And if we consider that circuit, because always that we have seen that if it is a given a Boolean expression, some truth table is possible, and if truth tables are possible, then always AND OR realization is possible. So, circuit wise this leads to a minimal 2-level implementation, and that is why this is very important in the digital circuit design. Now, see that here there is one circuit, simple circuit, the 2 AND gate and 1 OR gate, and the input of the first AND gate is the X. So, what this function realizes? The output Z realizes X dash Z dash, means the complemented of X and Z, plus X, this is a 3 input AND gate. So, X Y dash, okay, sorry, then Z is also a one variable. So, we change the output. So, this is function, this is a function f, simple function f. So, f equal to X dash Z dash plus X Y dash Z. Now, already we have read last class that standard forms. Now, in the standard forms only OR operations of each term exist, and each term must be a product of letters, what we defined as a sum of product. Now, what is the advantage? The advantage is the sum of product expression can always be implemented using a 2-level circuit. Just now one example we have seen. See, this is a standard form, this is a sum of product X dash Z dash plus X Y dash Z. Always this can be represented by AND OR gates. Now, literals and their complements at the 0th level, and AND gates at the first level, OR gates at the second level. So, if we see some hierarchy, say as if we are thinking that, say that literals, say A, B, C bar, they are at 0th level. Say these are my levels, and the first level, say as if AND gates are there or dot operation. In the second level, as if OR gates are there, that means plus, or if hierarchically we do, then as if this is my and these are my. So, it can be not always this can be more than 2 branches, say these are my literals, these are my literals. Now, see here A, B, so I take another one, say C bar. Here I take say A, C. So, what it will represent at this level? This becomes actually A dot C. This becomes A, B, C bar. Now, so this is in the 0th level, this is in the first level, and this is in the second level. Second level, this becomes A, B, C bar plus AC. So, this is my function f equal to ABC bar plus AC. So, this is the advantage, that always we can represent in this way, and if we represent in this way sum of product form, then always it can be implemented or it can be realized by the 2 level AND OR logics. Now, again another standard forms of expression, another example we take. This is a 3 variable function x, y, z, and the function is y dash plus x dash y z dash plus x z. See that, or that just now that example I have given. See, if I think that in the 0th level that it is y dash is there, then x dash, y, z and x z. So, in the first level it is AND. In the first level it is AND. See, it is only one literal, so as if it is ANDed with itself. So, 3 ANDs. So, this is my first level. Now, again these are in the second level, these 2 OR operation is there in the second level. So, this is my hierarchy. So, if I do this, actually the inputs are 0th level. So, that means this y dash, x dash, y, z, x, z, they are at the 0th level. These ANDs, they are at the second level, these are the second level, and the third level is that 1 OR. So, that means, so these are my first level, these are my 0th level literals, these are my the first level. See here, only one literal y dash is there, 3 literals are there, 2 literals are there, and this is my the second level OR. So, this is the way I can represent that thing. Now, already we have defined the min terms. This is a special product of literals in which each input variables appears exactly once. So, a function with the n variables has 2 to the power n min terms, already last day we have read. So, 3 variable functions such as f, x, y, z, these are the min terms. So, min terms are a dash, b dash, c, a dash, b, x dash, y dash, z dash, x dash, y dash, z, x dash, y, z dash, x dash, y, z, like all the terms. These are the all possible min terms. Now, already we have seen that these, if these are the min terms, means what do we mean? Last day we have discussed that this is the convention, that this is the if x equal to 0, y equal to 0, z equal to 0, that means one literal is 0, then it will be actually complemented. So, x prime, y prime, z prime or x dash, y dash, z dash means the 3 variables are zeros, and these, the decimal equivalent of these values is the subscript. So, this becomes m0. Similarly, we can do this thing. Now, the sum of minterms, that every function can be written as a sum of minterms, which is a special kind of sum of product form, and the sum of minterms from any function is unique. So, this is one property that only in one way I can do this thing. If we have a truth table for a function, we can write a sum of minterm expression just by picking out the rows of the table where the function output is 1. See, this is one example. So, these are the minterms, that all possible values I have taken. This is truth table x, y, z, and these are the output. See, there are two outputs, the function f function and f complement also. So, if say when that m0 terms means that x, y, z all are 0, then it becomes 1. That means my, if I write that terms, then this is my m0 equal to 1, then m1 equal to 1, m2 equal to 1, m3 equal to 1, and m6 equal to 1. So, as it is a sum of minterms, I can write my function is sum of 0, 1, 2, 3, 6. In this way we can write, and this becomes that if it is a 0th term means actually x dash, y dash, z dash. m1 means, because this becomes x dash, y dash, z dash. This 1 means this is x dash, y dash, z. 2 means this is x dash, y, z dash. 3 means this is x dash, y, z, and 6 means this is x, y, z dash. So, as this is a sum of product form, I can write all the OR of this thing, plus of this thing. So, this becomes x dash, y dash, z plus x dash, y z, y z dash, x dash, y z plus x y z dash. There are 5 ones in the f function. So, this will be the thing. Now, if we take the f complement accordingly, if we take the f complement, see here only m4, m5 and m7 exist. So, if I m4 in the expression, so f dash will be sum of 4, 5, 7. So, what will be the terms? Because 4 means 1 0 0, so this becomes x y dash z dash. 5 means 1 0 1, this becomes x y dash z, and 1 1 1 means x y z. So, my f dash becomes x y dash z dash plus x y dash z plus x y z. So, now we see how we can construct the kernel map, because we define that this is a graphical representation of where we can put that Boolean expression if the expression is represented as a sum of minterms. So, a 2 variable function has 4 possible minterms. So, these are the 4 possible minterms: x bar y bar, x bar y, x y bar, x y. Now we can rearrange these minterms into a Karnaugh map. Now see that if these are all possible combinations, or we can tell this is a rearranging of truth table. This is the truth table, that 0 0 0 1 1 0 1 1, and if it will be 1, it will in the second column it will be 1 if the function is such. That means that particular minterm will be 1 for these inputs. Now say this is a table. Now this table I can rearrange like that. Say this is my x is taking 0 or 1 value. X can take 0 or 1 value. So now this table I have rearranged as if, that means these are 4 combinations I have kept 2 by 2 form. So this is a 2 by 2 table. Instead of this table I am taking 2 by 2. So x can take either 0 or x can take either 1. Similarly, see here, y can take either 0 or y can take either 1. So y can take either 0 or y can take either 1. Now see, when xy is 0 0, the minterm is x bar y bar. So here in this table, say x is 0, y is 0, that means x bar, this minterm actually x bar y bar means m0. This is my m0. And if it is x equal to 0, y equal to 1, that means my 0 1 means x bar y. So this becomes x bar y. Similarly, if x equal to 1, y equal to 0, x equal to 1, y equal to 0, then this becomes xy bar minterm. So this is xy bar. Now if it is x equal to 1, y equal to 1, that means 1 1, this becomes xy. So actually these are the positions of the minterms for all possible combinations. Now we are telling this is my Karnaugh map. So this is nothing but the rearranging of the truth tables just to keep the minterms where the function becomes 1. Now we can is what we can do, that we can also write in this way. Say that if it is a 2 variable, again say x and y, say x and y, this 2 variable function. So how we are the Karnaugh maps we are writing, because x can take 2 values, either 0 or 1. Similarly, y can take, so if we put y here and we can put x here, then y can take also 0 and 1 here. So just now what we have seen, actually this is my y bar, this is my y, this is my x bar, this is my x. So this becomes x bar y bar, this is the position of the minterm x bar y bar. This is the position of the minterm x bar y. This is the position of the minterm x y bar, and this is my x y. Now say I have one function f equal to say x y plus say x y bar. So, that means what we have, this is first, this is a sum of product form. So, the minterms are this is x y means 1 1 means this is M3 and this is 1 0 means 2, that means M2. These two minterms are there. Now, how this K map will be, Karnaugh map will be there then? Say actually this is the position of M0, this is the position of M1, this is the position of M2, this is the position of M3. So, here we have seen that the product term, that means this product term or the minterm for these will be 1 and the function here it will be 1. So, that means M3 and M2, that last two will be 1 1 and remaining portions will be 0 0. So, this is the representation of this function. So, this is the Karnaugh map representation of this function f equal to x y plus x y bar. Now, we can easily see which minterm contains common letters. See, minterms on the left and right side contains y bar and y, just now we have explained, and minterms of the top and bottom rows are x bar and x. So, this is the, just now we explained that these are the positions of the minterms. Now, how we simplify? With this simple example, we see that how we can simplify this thing. So, again that two variable function if we take and see that the 4 terms or the 4 minterms are x dash y dash and x dash y and x y dash and x y. So, both of these minterms appear in the top position. That means, if I take a function f, so this becomes x dash y dash plus x dash y. And see here, if we can take x dash common, then y plus y dash becomes 1 and so this becomes x. So, in this way I can minimize that function. So, okay, today we will finish here, and next day we will discuss that how we can draw the Karnaugh map for the large number of variables or large number of literals.